Okay, so let us continue our lesson. So if you remember, I started talking about local maximum and minimum points or extreme points, and we'll learn that what is the relation between increasing and decreasing functions and how we can relate them to the notion of derivative. So do you remember what was that? So when the function is increasing and when it is decreasing, of course, the function is increasing. What is the definition, by the way? When we say that the function is increasing, what does it mean? Yes?
The slope is positive.
No, that is the consequence. What do you mean by a function is increasing? Actually, that's exactly in its name. Yes?
The further forward you go on the x-axis, the higher up the y-axis.
So when you go to the right, when you increase the value of x, the value of the function also goes up. This means that the function is increasing. And if you go to the right again, but the value of the function goes down, then it means that the function is decreasing. Okay? So sometimes, actually, you really don't need the notion of derivative at all. Okay? So for example, if I ask you, what is the behavior of this function, e to the power of x? Yes? Well, let me make it a little bit simpler first. If I ask you what is the behavior of this function, you really don't need to know derivative at all, yes? Because it is clear that when I increase the value of this x, the whole function increases, so that is definitely an increasing function, yes? Okay, so this is easy to take the derivative, and then how do you confirm it using derivative? Yes, that is the theorem. So the idea of increasing or decreasing is very simple. You increase the value of x, the function increases. This is increasing function. If you increase the value of x, the function goes down. The value of the function becomes smaller and smaller. That function is decreasing. If a function is decreasing or increasing, it's called a monotone function. Okay? And of course, it might happen that the function is increasing on one interval, decreasing on the other interval, which is most of the time. Yes? So here, you really don't need to know anything about the derivative, even though the derivative is very simple here. So if you take the derivative is 3x squared. So 3 is positive, and x squared is also non-negative. So if you multiply them, it is a non-negative number, and it squares with your intuition, what we learned before. Yes. For example, if I ask you this, what is the behavior of this function? Of course, here, if I ask Math 3 students, what is the behavior of this function? Of course, they cannot take the derivative of this function because they don't know the chain rule or they don't know the quotient rule. But even if they understand what's the meaning of increasing and decreasing, they can immediately answer that without understanding anything about the derivative here. So I just want you to understand the notion of decreasing and increasing is not exactly immediately related to the notion of derivative. We think harder, we connect these two together, okay? And the reason is that some functions are so complicated so that we cannot have this simple analysis that, okay, what happens if the function, when x increases? Sometimes in one limit, in one interval, when I increase the function, it increases. In another interval, when I increase the function, decreases. So keeping track of these behaviors are not that easy. So this is why mathematicians has tried to find a way out of it, and they immediately understand it by this geometrical picture that there is a very nice connection between the monotone behavior of a function and the notion of derivative. But let me ask you this one. You know the derivative of this, you can use the derivative, but what is the behavior of this function? Yes?
It's decreasing.
It's decreasing. You don't need to do anything, yes? When I increase the value of x, this is a fraction, its numerator is always a constant. When I increase the value of x, I am making the denominator bigger, so the whole fraction goes down. So this means that this function is decreasing all the time. But if you want to confirm that, let us use the product, the quotient rule. Yes, if I take the derivative, what happens? It becomes the derivative of the numerator 0 times the denominator minus the numerator multiplied by the derivative of the denominator. Yes, and then divided by 1 plus x squared. Okay, am I doing it right? Yeah, something strange is happening now. Let us see why this is working like that. So it becomes minus 2 what? Minus 2x, am I right? Divided by 1 plus x squared. Okay, so it is very strange. Yes, so our prediction was wrong. Yes. Okay, I have to correct myself. Why do you think it is the case? Because this function is not always positive. If x is positive, this is also positive. If x is negative, yes, because we were actually a little bit careless. I have to correct myself in the previous video as well. Because now, this is why I'm saying that. Even though the idea was simple, but you immediately see that this is not the case. Yes, because if x is positive, then the whole expression becomes negative. The denominator is always negative, always positive. So if x is positive, the numerator becomes negative, the whole expression becomes negative, yes? And if x is negative, the numerator becomes positive, the whole expression becomes positive. So why these odd behaviors happen here? Because exactly, I was a little bit careless when I was talking about this. I should have written x to the 3, not x to the 2. And if I had written x to the 3, then everything seems fine. No, again, everything becomes fine now. The reason is that. Why? Because if I ask you, this, I was also careless, especially in the previous, I have to correct that video. So if I ask you what is the behavior of this function, that was the mistake I made there. Because it seems that when I increase x, f of x also increases, but that is not totally correct. Yes? If x is positive and I increase x, of course x squared grows. But if x is negative, for example, minus 4 is smaller than minus 3. Everyone knows about that. But if I square it, it becomes 16, and this becomes 9. Then definitely this will increase, actually. So it means that on the right-hand side of 0, this is increasing. Below 0, it is decreasing. And actually, it squares with the graph, yes? Because the graph of this function is this one. Yes, so it is increased. So this mistake I made when I wanted to do this, okay, actually we fixed it here, but I didn't fix it in Math 3C lesson. Anyway, but if this is x to the 3, it doesn't matter if it's x negative or positive. When I am increasing x, it's always increasing, and the denominator becomes bigger, and then this quotient becomes smaller and smaller, yes? And then this confirms that, because now if I take the derivative is 3x squared, and then this becomes negative 3x squared, then this is always negative. Yes? Okay, so this is why you see that having a theorem is much more powerful than just a guess. Yes? But of course, if you're, what about this function? F of x is e to power x. Is this increasing or decreasing? Increasing. This is increasing, because if I start increasing the value, even for negative values, it doesn't change the behavior of this function. It always goes up when I go to the right. And for the same reason, this function is always decreasing, yes? Because another name for this function is 1 over e to power positive x. When I increase x, this value increases, so the whole value decreases, yes? But you see that even I made a mistake by prediction. So you see that having a mathematical tool in our hand is much more powerful, yes, than just randomly guessing something. Okay. So here we learn that if the derivative is positive, the function is increasing, and if the derivative is negative, the function is decreasing. I want you to understand the mathematical rigorous proof of that is beyond the scope of high school mathematics, but it is very intuitively clear, yes? If I have a function, for example, a mixture of increasing and decreasing parts. So for example, and by the way, if you have the graph of this function, this is a primary school task to see where the function goes up and where the function goes down. It's simple. Just by looking at the graph, we see that this part, the function is going up, this one going down, and then goes up. So even primary school students can immediately discover that. The logic, be careful, the logic is the other way around. We do not have the graph at our disposal. We have the formula for the function of the graph. We want to draw the graph of the function using the tools that we have learned in calculus, yes? Is that clear? So be careful about the logic. All these questions are trivial questions if you have the graph of the function. Okay, so here you see that at this increasing part, it doesn't matter which point I choose. This point, the graph, this tangent line is inclined in this direction, and you know that the slope of this is positive. And in this behavior, positiveness of a slope does not change. If I limit myself to the increasing portion, of course the slopes are different, but hopefully you see that all the slopes are positive. So it means that the derivative at the increasing part of the graph is always positive. Immediately when I go to the decreasing part, okay, and then what happens to the tangents are inclined like this. So it means that even though they differ from this one to this one, but of course all of them are inclined in this direction and all of them have negative slopes. And then from the previous lesson, we know that a slope is equal to the derivative of the function at the x-coordinate of that point. So if I ask you what is the derivative of this function at the point B, if this function is x, you immediately say that f prime of b is negative. If I ask you the same question for this, you immediately say that the f prime of a is positive. Yes? Okay, so, and then we learned about this. And then let me just remark you about this. Whatever we talk at Math 4 lesson in high school, we are always thinking about continuous functions and differentiable functions. Continuous functions are those functions that we can draw them with one pen stroke, and differentiable functions are those functions which doesn't have any sharp points. Yes. So of course, this will be, you will learn about these in the university. For example, even I will not talk about these type of functions. Even if I ask you what is this point for this function, you would say that this is a local maximum point. Yes, why? Because the height of this point is higher than the points in the vicinity of that point. But we are not able to discuss about these things. Actually, this is not part of your lesson. It is not too hard to discuss about these things. It's not hard, but it's excluded. So let me just stick to what is written in the book. So whenever I'm talking about the graph of a function, for most part of this, I will stick to continuous and differentiable functions. Yes. So if I give you a function whose local maximum point is a sharp point, you don't have the tool to detect that. Okay. Okay. So now today, and by the way, do you remember I talked about the first derivative test? What was the content of the first derivative test? Is that if you want to find the local maximum and minimum points of a function, you take the derivative, the first step. The second step, you equate it equal to 0. And then, for example, you get a point A. This point A is just a candidate for a local maximum or a local minimum or a terrace point. It is not clear that this is definitely a local maximum point or minimum or a terrace point. How we can understand that? That is the content of the first derivative test. What we do, we draw a table like this. The first row is x, the second row is f prime, the third row is f. And what happens? You put this number here, the derivative at this point is 0, the value of the function at that point is a. If this is positive, this is negative, it goes up and it goes down. So this is a maximum. Yes? And I don't know, let me just do it quickly. And then if you have this, minus positive, it goes down and it goes up, then it means that this is a minimum. But it might happen that the sign does not change at all, so the sign of the derivative. So here you have a, 0, positive, positive, it goes up, it goes up. Yes, it means that this is a terrace point. This is a terrace point of this type. And then if the other scenario is that this happens, I have x, f prime, f, and then I have f0 minus minus, it goes down, it goes down. So this means that I have a terrace point of this type. Yes? So this is the content of the first derivative. So this is very, very important to understand. Now I want to remind you what you learned in Math 3C again. That is called the second derivative test. Yes? Okay, is there any one of you remember the content of the second derivative test? The idea is the same. A function is given to me. I want to find all local extreme points of that function, but instead of the first derivative, I want to use what is called the second derivative. You remember anything from matrix C? Nothing. Okay, so let me talk about that. There is another test which we call the second derivative test. As you see the name, it deals with the f double prime, yes? But how we should work with it, you need to know it. But of course, the most powerful one is this one, because sometimes this test is silent. And that is the downside, the drawback of this test. Yes, this more or less can answer. This can answer if you work with continuous and differentiable functions. This can answer all questions that you have regarding the local extreme points and terrace points. But sometimes, unfortunately, this remains silent and cannot answer. But sometimes, if it can answer a little bit more quicker. So this is why I really want you to know about that as well. Okay, but before doing that, let me discover another behavior of the function, which somehow relates to the second derivative. So if let us just discuss about this situation, that I have a local maximum point here. Okay, so let us check one thing. If I want to see if I am working on this interval, say from A to B, you see that this is like an upside down bowl, yes? So it is, we say it is concave downwards, yes? It's concave downwards. When I say concave downwards, it means that it is like an upside down bowl. When I say it's concave upward, it means that this is just not like a normal bowl, yes? So here, I want you to see, if I start from this point, I have this tangent line. If I go here, I want to, this is the question. How can I, using the formula for the function, understand this behavior of the graph? You understand? A function is given to you with its formula, and just using the formula and the mathematics that you have learned so far, you want to understand, does this where this function is concave downwards and where this function is concave upward, yes? Something like that. So for example, you see that here, everywhere, this function is actually concave downward. How should I understand the concave downward property? It means that whenever you draw a tangent line, the graph of the function is below the tangent line. If the function is concave upward, if I draw the tangent line, the graph of the function is always higher than the tangent line that you draw here. So this is the difference between these two behaviors. Okay, do you see what is happening? Assume that I start going, I'm drawing these tangent lines. Of course, the slopes are completely different, but do you see any way that these slopes are changing? Are they changing randomly, or they are following a pattern?
They're decreasing.
They are decreasing all the time. Even if I pass that point, do you agree? Because this is positive, this is still positive, but less positive, yes? If I go a little bit higher, you see the tangent is a little bit like this, so it is still positive, but less. Until you reach to this point, which is 0, and then you pass through this, what happens? This becomes negative. So you must remember, you started with big positive number, you make it a smaller positive, until you reach to this one, which is 0. And then when you continue, it becomes negative, big negatives now. Yes? So this behavior is very easy to understand if you forget about the rules, okay? So when the function is concave downwards, it means that if I look at the slope of the tangent line on that interval, it is always decreasing. Is that understandable? Yes or no?
Yes.
Why not? You see that this slope is smaller than this one. It is steeper. Yes, this one is a little bit. So if you have a car, you want to go up here, it needs more energy than this one. So the slope of this one is this one. So if I go from this tangent line to this tangent line, the slope is getting smaller. Yes, and when I go a little bit higher, it becomes a little bit more horizontal. So the slope is becoming smaller. Exactly when I reach to that point, the slope becomes 0. And if I still continue, then the slope becomes of this type, which is negative. Yes? But then if I go down, the slope still remains negative, but the negative value increases. Again, it is steeper. Yes? So I started from, I would say, big, this in quotation, big positive, and then I go to big negative. Okay? But it doesn't go up and down. All the time, it decreases all the time. Yes? Until I reach to that portion when it is concave upward. Yes? From that point, then it is still, again, the slope starts increasing from negative to positive. Yes? So the moral is this. If I am dealing with the concave down part of the graph of the function, the slope of the tangent lines are always decreasing. And when I go to this concave upwards portion of the graph, this is always, the slope is always increasing. Okay? Now, do you understand how this will be related to the second derivative now? This is, by the way, very important even for physics, because you know that the acceleration is the second derivative. And then if you have the graph of those functions, and if you want to understand something about the behavior of the moving of the particle, you can look at this exactly concave upward, downward. So for example, if this is xt for a moving particle, yes? So at these points, the acceleration is negative. Yes, we want to come to these ideas. Okay, how this is related to the second derivative? Let me concentrate here and let me give it a name x. Okay, and let me write. Of course, my function is f of x, but I want to talk about a function, a slope of x. What does this mean? It means that if I give you the point x, f of x is how much? From here to here is f of x. Understand this, please. This is important. And then when I ask you what is k of x is the slope of this line. Yes? Of course, if I change the value of x, I go here, then the value of f, of course, is changing here. And the slope is the slope of this line now. So do you understand what is this function? This function gives you the slope of the tangent at the point x. Okay? Do you have a formula for this? What is the relation between k of x and f of x? This you need to know. Otherwise, we need to close the lesson today. Yes?
K of x is f prime.
X, exactly. Agree? K of x is f prime of x. Everybody understand that? Okay, now let us keep it aside, forget about this, and let us talk about the behavior of this function. By this analysis that I gave to you here, this function is increasing or decreasing on this part?
Decreasing.
It is decreasing, yes? Why? Because it was a big positive, it becomes a smaller positive number, and it becomes negative and bigger negatives. So k of x is decreasing, yes? But we just learned, if a function is decreasing, how is the derivative of this function? K of x is decreasing by this analysis. So can I say something about the derivative of k? It's negative. I agree. The derivative of k is negative. But what is the derivative of k? The second derivative of f. Understandable? So k prime is negative, but k is f prime. So k prime is f double prime. So this is why when you are on this part, the second derivative is negative. So, and then you can understand the same behavior. I don't want to waste the time. So here you will confirm that at these points the second derivative is positive. Yeah, please try to check that at home so that you understand what's going on. So the very simple lesson out of it, if you want to forget about these things, which I don't want you to do that. But anyway, what you need to know is that if the function is concave downwards if and only if the second derivative is 0 at that point. And it is concave upward at the point if and only if the second derivative is positive. Okay? Okay, but now this concavity is helpful to determine about the nature of this local extreme point, yes? If you have a slope equal to 0 and the function is concave downwards, what can you infer about the nature of this local point? Yes, just say it.
It's a local maximum.
It's a local maximum. Yes? So, two conditions. The slope is 0, so it means that I am facing this, but the second derivative, this is concave downward. So if the slope is supposed to be 0, it means that that should be horizontal. And if this is going to be concave downward, it should be of this type. So there is no, so this is definitely a maximum. Okay? Now again, if this is the horizontal slope, and then you have this behavior where the function is concave upward, then this is clearly a minimum. Is that clear? So that is the content of the second derivative test that I just want to write it here for you. So this is today's lesson now. Okay, so the second derivative test. Okay, so what should can you cook up the algorithm for me now? If I want to summarize everything, what should I do? What is the first step that I have to do? Yes? Just a step by step. F prime of x. Calculate f prime of x. Number 2. Yes?
F prime of x equal to 0.
Why? Because I want to see at which points I have horizontal tangent line. Yes? So these are candidates. But you know that you might have a fake one because you might have this situation. It's a terrace point. Okay. So f double prime equal to 0 and solve it. Yes, solve, let me write it like this. Solve f prime of x equal to 0. So let x equal to a be an answer. Okay, number 3. Can you continue?
Calculate f double prime.
Yes, calculate f double prime. Number 4.
F double prime of a.
F double prime of a, yes? What can you conclude? F double prime of a is what? Positive. F double prime might be negative. And that is the unfortunate thing that might be, we are very unlucky, that f double prime is also equal to 0. Yes? If f double prime is positive, can you conclude something?
It's a minimum.
It's a minimum because f double prime is positive. It means that this is concave upward. So it means that a and f of a is a minimum, is a local minimum. If this happens, then of course it is clear. It's a local maximum. Unfortunately, when this happens, the test is not inclusive. The test is silent, okay. What do I mean by silent? It means that we cannot draw any conclusion, okay? And I want to show you that this is, might be you don't think, you think that, okay, we still can draw some conclusions. I just want to give you 3 examples, very simple examples, to convince yourself that if this happens, you cannot draw any conclusions, okay? Let us check that. I'm just talking about why this is silent in this case. So if you are lucky up to here, you are done. If you get this, then it is not done. It means that everything you have done so far, these 2 steps, are actually spoiled. You need to go back to the first derivative test to understand what is the nature of that local, that point. Okay, so here, let me give you 3 examples. Let me consider these examples. F of x equals to x to the 4. So let me change the names. G of x, x to the 3, and then h of x minus x to the 4. Okay, let us consider these 4 functions. And you need to trust me on that if I draw the graph of function for you. A sketch, not the draw, okay? So here, I want to talk about the origin. First of all, do you agree that all these functions are passing through the origin? Yes? Because if I put x equal to 0, y becomes 0. If I put x equal to 0, y becomes 0. If I put x equal to 0, y becomes 0. So it is clear that all these functions passes through the origin, okay? If you trust me on that, if I draw the graph of this function, you will see something similar to x squared, but more steeper, okay? And if you draw the graph of this function, you will get this behavior, okay? And then if you draw the graph of this function, can you guess? No. Why? Because this is the negative of this one, so it would be upside down. Yes, thank you. So in principle, they are exactly the same shape. Forget about that. I cannot draw them precisely. But now let me ask you, what is the nature of the origin for this function? Everyone, yes? What is that? Local minimum. What is the nature of this point? A terrace point. What is the nature of this point? Maximum. So here, minimum, terrace, okay, and then here, maximum. But let me check. The derivative of this function at 0. Let me calculate the derivatives. Then the second derivative. This is 4x to the 3. This is f double prime of x is how much? 12x squared. Yes? Now, what is f prime of 0? It is 0. What is f double prime of 0? It is 0. Yes? So it means that the first derivative is 0. And the second derivative is 0, but the nature of the point is a minimum point. Yes? Let us check this one. The first derivative of this function is 3x squared. The second derivative is 6x. If I ask you what is the first derivative at that point, it becomes 0. What is the second derivative is again 0. Yes? So you see the first derivative is 0, the second derivative is 0, I have a terrace point. And then if I go to this function, I hope that everything is clear now, h prime of x is minus 4x cubed, and h double prime of x is minus 12x squared. If I calculate h prime of 0, it is again 0. If I calculate h double prime of 0, it's still 0. So what does it mean? It means that if on top of that the first derivative is 0, the second derivative is also 0, everything is possible. Yes? It might happen that I have a minimum point under these conditions. It might happen I have a minimum terrace point under these conditions. And it might happen that I have a maximum under these conditions. So this is why if you are unlucky, and if above f prime being 0, f double prime is equal to 0, nothing you can conclude, unless you have extra information. So then the question is that, what can I do about this situation? It means that the energy that at the time that you have used from this step to this step for this point does not work. And then you have to go back to the first derivative test. That will work. Okay? Is that everything understandable? Okay, let us just try to solve some examples using this idea. Okay. If you don't want that, let me keep it here. I want to clean this one. Yes, is that okay? Okay, so let us see how we can solve these problems. So example, let me see what to choose. Let me choose one. Use the second derivative test. Use the second derivative test. Of course, I would write if applicable. To determine local extreme points of the following functions. Determine the local extreme points and the nature of those points. Of course, for the following functions. The nature, it means that is it a maximum or is it a minimum? Or is it a terrace point? Of course, the terrace point cannot be answered using the second derivative test. And I think these examples are those examples, if you go back, watch the video or see the lecture notes, these are the same functions that we did before using the first derivative test. We didn't have time to finish it that time. It was good if we can compare the methods. So anyway, you can go back and see my lecture notes that I have uploaded below the video on the YouTube, so that if you want to compare to see which one is easier for you to use. Okay, so let me write A and keep these numbers 1, 2, and 3, 4 for here. A function is given to you, and then you are supposed to determine the local extreme points. The first step is to calculate the derivative, which is 3x squared minus 6x minus 9. The second step, I have to put it equal to 0. So then this means that 3x squared minus 6x minus 9 is equal to 0. And I think it would be better if I divide by 3. It becomes x squared minus 2x minus 3 is equal to 0. You can use ABC, PQ formula, but I think it is not hard for you at this level to factorize this. I need two numbers, so don't get confused. If you are not happy with this method, just use the PQ formula, okay? So I need two numbers whose sum is minus 2 and its product is minus 3. Can you guess those? Yes?
Minus 3 and positive 1.
Minus 3 I put here and positive 1 I put here. The sum is minus 2. The product is minus 3. So this is the way that we factorize it. If you don't like it, you just go and solve it using PQ formula. Equals to 0, and then either this one is 0 or that one is 0. So this gives me x equal to minus 1 or x is equal to 3. These are the numbers. So the second step, the third step is done. What was that? That was the second step. The third step, calculate the second derivative. It is mentioned in the problem, use the second derivative. So number 3, f double prime of x, I calculate this. F double prime of x is another derivative from here, which is 6x minus 6. This is my second derivative. And finally, I go to number 4. In number 4, I calculate f double prime for those values that I found in this step. So what I do, I calculate f double prime of minus 1. I put minus 1 here, it becomes minus 12, which is negative. So what does this mean? This means that minus 1 and f of minus 1 is a local maximum. Yes, if it is negative, it's a local maximum. And I don't want to spend time on it. Calculating f of -1 is simple. You just put -1 here and calculate it, and you put it here. Yes. And then I need to check f double prime of 3. Be careful. Put it in the second derivative. I put it here. It becomes 6 times 3 minus 6, which is positive 12. Because this is positive, it is not silent. I can draw some conclusion. Point 3 and f of 3, which I don't want to calculate, put 3 here, is a local minimum. Yes? Is that understandable? Okay. If you go back to see the video or the lecture notes, I have solved this problem using the first derivative test. And if you compare them, that is up to you which one is easier. Of course, if you have a polynomial function, I myself prefer, because taking the second derivative of a polynomial function is easy. But assume that you have a complicated fraction. Yes? And then if you want to take one derivative, it becomes even more complicated fraction. You want to do one more derivative, it means that you need to work harder. So this is not guaranteed that this method is always beneficial, but you have to know about them because they can ask you some questions that you have to use this. For example, they just give you information about the sign of the second derivative and the function itself is not given to you. And they are asking you about the behavior of the function. If you don't know this theorem, then you don't know what to do, okay? So you need to know the content, but that is up to you if you have options, which one to use. Okay, any questions? But let me give you another example. We also solved this in the previous lecture using the first derivative test. Hopefully you know what is going on here so I can clean it. I am going a little bit fast probably, but all of these are repetition in matrix C in principle, yes? Okay, so what is this function? Now, part B, f of x is equal to 3x to the 4 minus 16x to the 3 plus 24x squared, and then I have minus 9. Okay, so let us do it. The first thing I need to do is step number 1, I take the derivative. The derivative is 12x to the 3 minus 48x to the 2 plus 48x. The second step to equate this derivative to 0. Okay, so this means that 12x to the 3 minus, that is degree 3, okay? And then this is 48x equals to 0. For third degree equations at the level of your lesson, of course, even in higher levels, there is only one way to factorize it. But at the level of your lesson, if I'm going to give you a question, the factorization is simple. Of course, it might happen that this factorization is very hard. But here, I think everyone knows how to factorize this. We immediately see that 12x is in common, so I can take it out, yes? So this means that 12x is pulled out, so this is x squared minus 4x, and then I have plus 4, yes? So I put it equal to 0. And then how many answers do I get? By the way, this is also a quadratic pattern, so let me just use it. So 12x, this becomes x minus 2 to the power of 2 is equal to 0. So then this means that either this one is 0 or that one is 0. So this means that either x is equal to 0 or x is equal to 2. Understandable? Okay, now we go to the second derivative. When I take the second derivative, I take it once more from here. So what happens? It becomes 36x squared minus 96x plus 48. And then finally, I go to a step number 4. I calculate f double prime at 0. F double prime at 0 is super simple to calculate. It is 48. And it is positive. So this means that the point 0, f of 0, by the way, f of 0 is simple, let me write it. F of 0 is minus 9. Let me write it if you want to see it in the future. F of 0, which is equal to 0 and minus 9, is a local minimum. But let me calculate f double prime of 2. What happens here? F double prime of 2, it means that I need to put here. So 36, 2 to power 2 is 4, minus 96 times 2, plus 48. 144, yeah, that is 0. And this is the unfortunate thing that happens. The second derivative turns out to be 0, so I cannot draw any conclusion here. No conclusion can be made. Conclusion can be drawn. So it means that if you really insist to understand the nature of this point, you have to go to the first derivative test. Yes? And okay, can you immediately say that what type of this? Because of course, I made it big because I wanted to solve it completely, but you really don't need to go through all those details. Every information you need on the board is also there. So you understand at this point that second derivative is silent for this. But first derivative, so it means that let me go back to the first derivative. And if you see the first derivative, in this form, it seems a little bit complicated. But do you see that I haven't simplified anything? I have just changed the form of the function. It becomes like this. Yes? But now can you tell me, by looking, because this is the derivative, this is the first derivative. Can you draw any conclusion regarding 2 now? Yes?
It's a terrace point.
It's a terrace point. Why? Because x minus 2 to power 2 is always positive, yes? Because of this power 2. And then when you are talking about 2, you are a little bit before 2 and a little bit after 2. A little bit after 2, of course, this is always positive. This is also positive. So if this is 2, after 2, the first derivative is positive. Before 2, this again is positive because of power 2. Of course, if you go very far away, it becomes negative. But if you are close to 2, and this is also positive. So it means that close to 2 on both sides, you have positive sign. So it goes up, so it means that that is a terrace point. Is that understandable? So that is, I want you to understand the content. You have to decide which one is suitable for your case. Yes? So when we wanted to understand the second derivative test, we also learned something very important, and that was the notion of concavity. So this is something we also learned. How do we understand the function is concave downward? We take the derivative, the second derivative, and put that point there. If it turns out to be negative, it means that at that point, the graph of the function is below the tangent line, so it is concave downward. If it is positive, it is concave upward. So that is also one thing that I want you to learn, okay? And there's something we learned in Math 3C, and that was the notion of inflection point, okay? So what was an inflection point? Do you remember? Yes?
It's where it transforms from concave down to concave up,
or the other way around. So the concavity of the function at that point changes. An inflection point also we use in, for example, we can say that the Second World War is an inflection point in human history, okay? So that's more or less the same thing. It means that a radical change is happening here, but of course the radical changes is much, much milder than the Second World War. What happens is only that the concavity of the function is changing, okay? Okay, so here I want you to understand that one, because this is the third algorithm. If you don't understand them, because these are not in the formula sheet, so you need to know them by heart. And because there are 3 algorithms somehow close together, there is a high chance that you mix them up if you don't understand them, okay? So what is an inflection point? So as Sanders told, so you see that here we have 2 situations. By the way, so far we have we talked about inflection point, but with a different word. Do you know what was that? Yes? A terrace point. A terrace point is also an inflection point, but a particular form of an inflection point. Yes? So here, so I want you to understand the difference. People, I don't know, I hadn't seen this word, by the way, before studying a Swedish curriculum. Okay, what I knew was just inflection point. But I think this distinction is good now. Because do you agree that this is also an inflection point? Because if I ask you what is the concavity before, it's downward. Immediately after that, the concavity is upward. But there is an extra property, and that is the tangent is also horizontal. So a terrace point is an inflection point at which the tangent is horizontal. But I might have this situation, if I can draw it somehow good. So I hope that you understand somehow that this is an inflection point. But here, if I draw the tangent, yes, if I draw the tangent is not horizontal. But again, you see what is happening. On the left-hand side, the graph is below the tangent line. On the right-hand side, the graph is above the tangent line. And this is also happening here. Before this point, the graph is below the tangent line. Immediately after that, the graph is above the tangent line. So that is actually inflection point. So a terrace point is a special form of an inflection point at which the tangent line is horizontal. Yes? Okay, now, can you tell me, just I want you to cook up the algorithm yourself. How can I detect this point? Of course, again, if you have the graph, it's a little bit hard for primary school, but probably intermediate school, the student can detect it by looking at the graph. But how should I detect this? By using the formula. For example, I just give you a formula, and I ask you to find, if any, inflection point for this function. Can you cook up the algorithm? The reason that I am asking you to cook it up, because finally you need to have it in your brain. Yes?
We set the second derivative to 0.
Okay, yes, and then? Is it guaranteed that the point that we get is definitely an inflection point? Do you see, do you remember this example that I gave you? Do you remember? X equal to x to the 4. Yes? If I take this first derivative, it is this one. If I take the second derivative, it is this one. If I put it equal to 0, what I get? I get x equal to 0. But do you believe that that's an inflection point?
No.
No. So again, the same story happens. Exactly, very similar to the first derivative test. Be careful not to confuse them. In the first derivative test, you take the first derivative, equate it to 0, and you get some numbers. Those numbers are just candidates for local extreme points. How we did understand which one is correct, which one is not? At that point, we had two options available. Either use the first derivative test to understand the nature, or the second derivative test. But when it comes to inflection point, so you see that taking the second derivative and equate it to 0, just give me the possible candidates for inflection points. There is no guarantee that what you get is a real inflection point by this example. Clear for everyone? Okay, now how can I get rid of this situation? How? No idea. Yes?
You put up a table and like do as you would have done with the first derivative test instead of with the second derivative.
Yes, that's correct. And it will work. Why? Because why this is a fake one? Because the concavity doesn't change. Yes, even though the second derivative is 0, but if I ask you what is the concavity of this function before 0, you say that is upwards. What is the concavity after that? It is again upwards. So it means that concavity is not changed. If I ask you what is the second derivative on this portion, you say it's positive, it's concave upward. Even when I pass this point, the concavity is again upward. But here, the concavity is downward immediately when I pass through this point. Yes, before that the concavity is downward, after that the concavity is upward. Yes, so this is the important thing. So if you take the second derivative and equate it to 0, you just get the candidates of the inflection points, and that is a very good thing to do, because before that, how many options in potential are available here? Infinitely many. How should I know which one is correct? But by taking the second derivative, I narrow it down to a limited number of points, and then I have to check the sign of the second derivative. If the sign of the second derivative is changing from negative to positive, or from positive to negative, it means that this is indeed an inflection point. If that's not the case, that is not an inflection point. Is that understandable? Yes? So, and then you see that why this is not an inflection point. Because this is the second derivative. If you put x negative, this is a positive. If you put positive, it's still positive. So the concavity is not changing. So this is how you can detect. So if I want to cook up an algorithm here, so how to detect inflection points. By the way, these things that I am talking, if you go to a technical university, whatever effort you put right understanding these things will save you a lot of time in the future. And by the way, if you go to technical universities, I don't know, you need to study nearly 1,000 pages in 14 weeks. Okay, so be careful. And then you are not allowed to use calculators. You're not allowed to use computers in the exam. You're not allowed to use formula sheet in the exam. Okay, which is a formula book actually then, but you're not allowed to use it. So please try to understand them. Yeah, because I know that usually when you are in the high school, you just want to get rid of this stage. Okay, I want you to correct it in your brain. This is not just passing through this stage and reach to the university, because the story immediately starts. Okay, so if you want to go to university, you need to enjoy what you are doing. Otherwise, it's better not to go there. Okay, especially in Sweden, you have a lot of opportunities to enjoy your life. If I do this because I enjoy this, if you don't enjoy this, forget about that. Okay. So here, let us cook up an algorithm. Okay, so how should I write the title? Detection of inflection point or points of f. Okay, so what should I write first? Of course, I have to take f prime of x, yes? Determine f prime of x. Second, determine f prime of x, f double prime of x, yes? Number 3, put it equal to 0 and assume that you solve this and you get a. I'm just summarizing it. This is here a possible candidate for the inflection. Okay, so now you need to set up a table. But this table, as Alex told, this is x. This is f double prime instead of f prime, or f. And then you write here a. Of course, f double prime here is 0. So if this is, by the way, you really, yes, because you also need to count. When you say point, it means both x coordinate and y coordinate. Okay. So if this is positive, positive. No, sorry. If it is positive, negative, then a and f of a is an inflection point. Okay, another scenario is this. You have x, f double prime, f, a, 0, f of a. You have negative, positive. Again, the same conclusion. If you face these two situations, you have that. If both of them are positive or both of them are negative, then you can draw the conclusion. The conclusion is that no, this is not an inflection point. It means that if this is the only answer from here, there is no inflection point. If there are other answers, you can also add those answers in this table. and then draw conclusions for them. Okay, so let me just do that. So I have x, f double prime f, I have f here 0, positive, positive, f of a, or I have this table, x, f double prime f, a 0, negative, negative, f of a. And from these two situations, a and f of a is not an inflection point. Yes? Yeah, okay. Is that understandable? Of course, there is also another algorithm that you need to have in mind, and that is related to optimization problems. Okay, I don't know if, are you tired? No? Yeah, okay. So we can also talk about that one as well, so at least we get rid of. So all these things, ideas, are compacted in 1 or 2 pages in the book, because they are assuming that you have studied everything like this before in Matematik. Okay. Yeah, I think we can have a little bit of a rest, 1 or 2 minutes, so we can start the new topic. Before starting a new topic, might be a good idea to give an example that you couldn't solve in Matematik. Let me try to think a little bit about that. Yeah, this chapter is a very, very long chapter. So make sure that you study with me.
Jag fattar inte frågan. På änden av verksamheten. Nej, i sensorn gör det inte det. Ja, precis. Måste sensorn agendaskapet gå eller vara här? Nej, jag det är spännande på det är en klubb. I början som är spännande. Nej, men det finns sensorn gör mitten på axeln. Det är följer och så kan axeln gå dit och
Det beror på.
Du pratar om motor neurons. Ja, de går in. Men sen så ser annorlunda. Då frågar jag, sen går det alltid i spannet. Det betyder då går sensor neurons liksom en går att ta det, en går att ta det. Jag kan inte göra
Det verkar som att den är utanför. Det här är utan.
Och det är
Ja, det verkar
effekter. Och så är det effekter. Och det finns
just det. Vart stod det?
projekt. Så typ jag vet inte, pain receptors.
Okay, so let us start. Let me give you an example before leaving this section. This, in principle, Math 3C students cannot solve because they don't know how to differentiate this function. But otherwise, everything they have learned is the same. Okay? So I want to determine the inflection point or points, if any, of this function. So what should I do? The first thing that I have to do is to take the first derivative. The first derivative needs the chain rule. So what is the answer? Is the derivative of that, which is this function, multiplied by the derivative of the exponent using the chain rule. Yes? So the answer becomes minus 2x. Let me write it on the left-hand side. E to power minus x squared. Then I go to the second derivative. The second derivative is a combination of the product rule and the chain rule. Yes? So here I have a product. For this one, I need the chain rule. So what happens? The derivative of the first one, minus 2, multiplied by the exponential function, plus the first part, multiplied by the derivative of this one. But the derivative of this one is exactly as before, so let me just write it down. Yeah, is that understandable for everyone? Let us simplify that because we want to work with it, okay? So it would be better if I can simplify this a little bit. So here, first of all, you see that I have e to power minus x squared, e to power minus x squared here. And I can factor it out. And then from here, minus 2 is left. Minus 2x multiplied by minus 2x is positive 4x squared. And then this is pulled out. So this is my derivative. So let me put it in a compact form here. So I will have 4x squared minus 2 times e to power minus x squared. So this is the second derivative. It is similar to one of the exercises in the book. I don't know exactly, but this is something that you need to do, be able to do it at this level. Okay, and then do you remember, first I need to find the candidates. The candidates are coming from putting the second derivative equal to 0. So don't get confused. Once we use second derivative for understanding the local extreme points, now I am using the notion of second derivative to talk about the inflection points. Don't get confused. Okay, so f double prime is equal to 0. Then what happens? This means that for x squared minus 2 e to power minus x squared is equal to 0. So the product of these two numbers is supposed to be equal to 0. Either this one has to be equal to 0 or that one. But the right one cannot be equal to 0 because that's an exponential function. This is always positive. Even though the exponent is negative, but it doesn't matter. This is always positive. So this means that the first factor should be equal to 0. And that is easy to solve. I move 2 to the right, divide by 4. It becomes 1 over 2. And then what is x? X is 1 over square root of 2 plus or minus. Yes? But what are these? These are just candidates for possible inflection points. What I can conclude right now is that if this function is supposed to have an inflection point, it has at most 2, yes? But there is no guarantee. It might have nothing, it might have 1, or at most 2. How should I understand that? I need to set up a table. The table is very similar to the first derivative test, unless you have the second derivative here, and you have f here. So in principle, this means that this goes from minus infinity to infinity, even though your book doesn't write it. There are two numbers, so I put them in order, from smaller one to the bigger one, yes? What happens for the second derivative at these 2 points? I myself put the second derivative to 0. I got those numbers, so it means that if I put them, this becomes 0. Yes? And then I need to determine the sign. Do you have any suggestions? What is your second derivative, by the way? This is your second derivative. I want to see where this is positive, where this is negative. The second derivative test. So how should I do that? First of all, you don't need to be worried about this part, yes? Because this is always positive. So if this is going to be negative, this is the important point. If this is going to be positive, again, this matters, yes? So it means that you can, for the sign, you can momentarily forget about this and just concentrate here. And do you remember I told you a trick and a technique how to understand this? Do you remember what I told you when I was teaching you the first derivative test? You remember a lot, actually.
Yes, sir.
Yes? A random number from that interval. I choose a random number. For example, what is a good random number between these two?
0.
0. I put 0 in the second derivative. It becomes -2 times 1, which is negative. So by the way, I want to ask, I remember I didn't talk about why this is correct. I put a negative sign there. Okay? And then if I go before -1 over the square root of 2, do you agree which one is better to choose? -1. If I put -1 here, this is always positive. This becomes 4 minus 2 positive. So this is also positive. And after that, it is also positive. Don't write up and down. There is no up and down here. Okay? But if you want to insist writing something, do something like this. So it means that below this, the second derivative is positive, so it's concave upward. The second derivative is negative, it's concave downward. And this is also concave upward. But if you want to, you need to answer these numbers as well. How should I answer these numbers? I can feed these numbers into the original function. Yes, because this is the line for f. If I put -1 over, let me put this one first. 1 over a square root of 2 here, what happens? It becomes e to the power of -1 over 2. Do you agree? This would be the answer. And this will give me the same answer here. Of course, if you want to make it more beautiful, it would be like this. Yes? So are these points fake inflection points or they are real inflection points? They are real, because you see that the second derivative is changing the sign in passage of these points. Yes? So how many inflection points are there? 2 of them. One of them is -1 square root of 2 and 1 over square root of e, and 1 over square root of 2 and 1 over square root of e are inflection points. Yes? And if I remember the graph of this function, the reason I was able to cook up is because I remember this is more or less this is Gaussian bell curve, something like this. So if you draw this, this is y equals to e to power minus x squared. This point is 1, because if I put x equal to 0, it becomes 1. And you see that these are inflection points. Yes? So here, this is concave downward and suddenly goes upward. And it is clear this is completely symmetric. This is why one of them is this and the other one is this. Yes? So these are the shapes. So what we have done is completely according to the graph. Yes? But I hope that if you draw the graph by GeoGebra, just by looking at the graph, you should immediately understand that there are 2 inflection points. Yes? Even if you don't know what are those values, by seeing how the curve, how the graph curves, you need to understand that there are 2 inflection points. Okay, then let me not start the new lesson. You are not actually very alert, probably. But why is it? Do you think that there is a why going on? Nobody asks about these things. So why do you accept this from me? How many numbers are there between minus a square root of 2 and 1 square root of 2? Infinitely many. But I randomly chose 0. And I fit that 0 into the second derivative. It turned out to be negative. And I claimed for you, okay, everywhere else it's also negative. Do you think that this is trivial? Because you didn't ask any question. Is that trivial? Do you understand that there is at least a question there? Yes? Because when I write this big, why do I write this big negative sign? It means everywhere between these, I am saying this is negative. But did I test everything? No, I just checked one single. Why do you think that this will work?
Because there would be an inflection point otherwise in between those two, where you can make an inflection point.
No. Negativeness and positiveness I am talking.
Oh.
Yes, Louis, you want to say something?
Well, if we assume that it's not negative all the way there, then we would find another candidate.
I think you said the same thing. Yeah. So that is more or less correct. Yeah. So you have to find another candidate there. Yes, because if this sign is going to be changed somewhere in between, yes, so there should be an inflection point, because you are telling me that the sign of the f double prime is changing somewhere. This is one idea. The second idea, which always worked, and that is very good to know, is this. The reason is that if this function of I forgot to not clean it. This was the second derivative. Okay, this function is an exponential function multiplied by a polynomial function. As an extra information, remember that exponential functions of this type are continuous functions, and polynomial functions are continuous. And when you multiply two continuous functions, the result is still continuous. And then what is the very important property of the continuous functions is this. If I want to go from this point to that point continuously, I have to cut the x-axis somewhere. Yes, I go up. I have to. It doesn't matter if I go down or go. If I want to reach to this, I have to cut it. Yes. If this is discontinuous, this is not the necessity. Yes. If I can have a discontinuous graph and I want to go from here to here, I can come up to here, then jump here, and then continue without cutting the x-axis. Okay. Now let us check about this function to see what type of function is that. Forget about the details of the graph. What I want you to know is that the graph of that function is a continuous function, and let us just draw a continuous function. Okay? So you see, if these are the intersection points, these are the roots. You see that the continuous function behavior is like that. If these are two consecutive roots of a continuous function, what happens? Either the whole function between these 2 points is above the x-axis, it's always positive, or it is always below the x-axis, it is always negative. So if I choose one random point here and calculate this one only, and it becomes positive, it remains positive between these two. The only way that it can change the sign is going to the next pair. Okay, so this is why, because this function is continuous and I checked one random point between these two and it was negative, it guarantees that it remain negative until I reach to the next point. Yes, and that is the idea. Even you go back to the first derivative test, if someone asks you why this is working, you need to tell that this highly depends, this argument highly depends on the continuity of the function that I have in this row. If the continuity is not there, this argument might fail. Is that understandable? Yes? Okay, so I can stop the lesson here. Thank you for listening.